Welcome back to the morning show. It's 6:48. You need more than a ruler to measure the speed of light.
We've tried everything from crystals to egg, but this week the wise guy is getting fancy. How will you measure the speed of light? This week, Matt, good morning.
Hi, Jennifer. Hi, Robert. How are you this morning?
We're good.
So last week, you might remember, we did a kind of a cheesy measurement of the speed of light using a microwave oven and an egg white, and it sort of so-so didn't quite work, but it wasn't too bad. It was okay. And then we measured the speed of an electrical signal in a cable using this very oscilloscope that we're going to use here in a moment. But today we're going to do this right. We're actually going to send a pulse of light through a known distance, and we're going to see how long it takes for it to go across that known distance, and then therefore we're going to measure the speed. So the speed is just going to be the distance divided by the time it takes. And we have the world's expert on lasers here at the U of I, Professor Paul Kwiat, who's standing right beside me, and he helped to put together this beautiful experimental setup that you have here. And so let me explain what you got. This looks a little more professional than the egg white in the microwave, you'll have to admit. So we have here a pulsar that sends an electrical signal to a laser diode, which is located right down at the bottom here. And then this little red cable is actually a fiber optic fiber that takes that light and makes it shine out in this direction. It hits a mirror, which is right over here where my finger is. It then goes down to this mirror, bounces back to this mirror, and is detected over here. And what we're going to do is we're going to move this mirror back and forth, and we're going to see that the amount of time it takes the light to make that round trip increases as we move the mirror to your left and move it back again to the right. So Paul's going to help me by going around to the front. What we have here, just let me explain. On the oscilloscope, this is the same thing that we had last week. The pulse that you see on the top trace, you see the thing go up and come back down again, that represents the laser light pulse as a function of time, where time increases to the right in this picture, and each one of those little divisions is a few nanoseconds right now. So what Paul is going to do is he's going to move this mirror over by 2 feet, and you're going to be able to see that pulse move to the right. And so you see how it moves over to the right a little bit? If we measure very carefully the distance that it's gone, then you'll see that it just went over 4 nanoseconds. That's 4 1/billionths of a second. That's a very short amount of time extra that was added on by making this mirror move from over here to over here. But the reason it takes 4 billionths of a second more to go from this whole distance than just from over here is that we added 4 feet to the path length of the light. Okay, so light does travel 1 foot every nanosecond, and we'll come back and we'll show some other ways that we can make light actually slow down a little bit.
All right, thank you, Matt, for that. We've got the setup. We're all ready to go. We know how it's going to be measured.
A foot every nanosecond. I always knew it was like 186,000 miles per second, but a billionth of a second it goes a foot.
A billionth of a second.
That's cool.
And now that we've got the world's foremost expert there, too, it's nice. We have the experts telling us this.
It's 6:51. We're hitting the slopes this morning, and we might just find Frosty the Snowman in this morning's postcard.
Plus, companies are luring you to